Ariel Rokem, and today I'd like to talk to you about yet another tool that I've come to love over the years called scikit-image, and how we can use that tool to do image processing and computer vision. So I've prepared a couple slides for today to walk you through some common concepts in image processing and in computer vision, but the main goal is really to introduce scikit-image, a toolkit that can be used to do various things, mainly manipulate images in Python. And we want to go through some of its functionality, focusing on two different topics, one being feature detection, which is talking about how we can analyze images and sort of detect and extract interesting stuff in there. And the other thing is image segmentation, where we want to label different regions of the image accordingly. So I'm curious, how many of you have heard about scikit-image already? And how many use it regularly? Okay, cool. And we'll get to more about that later. First, we should probably talk about what is computer vision. And I'd say it's an interdisciplinary field that tries to gain information about images, extract understanding from digital images or videos. So it's all about how do you acquire images, how do you process images, how do you analyze them, how do you make sense of things. If you think about the difference between computer vision and image processing, we can argue all day, but roughly speaking, image processing is really about an image-to-image transformation. Some image in, you do some stuff, you get an image out. Whereas computer vision is more focused on getting descriptions out. Image in, and then maybe you get segmented regions out, or you label an object in the image, stuff like that. And so if you want to do computer vision, you probably need a bunch of different techniques and methods, maybe from signal processing or pattern recognition, as I've just mentioned. There's some image processing in there, so I would consider computer vision probably a superset of image processing, or at least adjacent. And more, it's also about machine learning, or what is labeled here, artificial intelligence. But we probably won't get to that today. Yeah, so what is image data? I'm going to talk about images. I think everyone knows what images are intuitively, but how can we define image data? How is that distinct from other data that you know, maybe like time series data? Does anyone have a guess? What's the thing about images that makes them images? Say again? Spatial, yeah, something about. So it's about the spatial relationships in that data, where you can think about it in a local neighborhood, you treat these pixels differently than pixels that are far away. And that's usually what separates images. So it's about spatial contiguity. Yeah, and usually we deal with 3D images or 2D projections, but you can also have higher dimensional images, right? Where each dimension is maybe a channel of an image, depending on your transform. All right, so why would you care about computer vision or image processing? How does it apply to neuroimaging or medical image analysis, for example? And here's one little toy example I grabbed from the scikit-image tutorial, so don't go crazy about this. Imagine you have an original image, and you got this image maybe from two different stains, a stain and a counter stain. So you have mixed color information in there. And maybe if there were a way to sort of deconvolve, get out the different color channels, you could look at this image through different lenses if you want, and extract the immunohistochemical that was used to stain. Another example might be image registration. So imagine you're taking a bunch of MRI slices over time, and over time maybe the subject moves, maybe there's noise, maybe the images just don't look the same. How do you correspond pixels in different slices to each other? So there are various techniques to do that. What's shown here is a thing called feature matching, where the idea is you look at the left image and you find interesting regions, and you try to find the same regions in the other image. And then you combine the two, draw a line between them to establish correspondence. And that allows you to bring the two images into a common coordinate frame. A little more advanced, maybe you don't just want to process images, maybe you want to reconstruct a world from it, or reconstruct a 3D brain structure from it. So here we have 3D white matter tracks extracted from diffusion tensor imaging, which is pretty advanced stuff. There's other things that are starting to combine machine learning, or in this case deep nets, with different computer vision techniques such as segmentation. So what you're looking at here is a slice through the retina. And you can see here the different layers of the retina. On top you have the ganglion cell layers. On the bottom you have photoreceptors. And what this algorithm does, it labels regions in there that correspond to an edema, to like fluids that are stuck between cells, which is very important for pathology. And this is actually code based on work by Ariel Rokem. You can get it from GitHub in collaboration with the medical department at UW. So this is really, really advanced stuff where you combine like textures of different images in a deep hierarchical net to then classify patches of the image as either containing an edema or not. So there's a lot of fun stuff you can do. I hope this loads. Let's see. So here's another example where a 3D model was reconstructed of this brain hemisphere, and you see different regions of the brain labeled with different colors. So you can shift click on here, and here will tell you here label which region it is. So we're looking at the lateral occipital lobe, and you can play with this and look at it from all possible perspectives. So the only reason this works is that there was some inference going from different images into a 3D model of the brain, right? But today we won't be able to get to such advanced techniques. What I still would like to do is introduce you to the basics, the foundations of image processing. On the example of scikit-image, which is a toolkit, a collection of Python algorithms that allow you to do image processing developed by the SciPy community. And you can install it with Conda. If you follow the early tutorials and you downloaded and installed Python on a Conda, it should already be installed on your machine or on the hub. And you can find out more about them at their website. So what can scikit-image do? It provides a whole bunch of different methods to mess with images. For example, on the top left, you can see an image of a bunch of coins, and you can apply morphological operations. You can it's called delete, so kind of, what's the word, like enhance different regions of the image or fuse them together. You can do filtering, where maybe you're looking at a page of text and you're trying to extract just the text or just the background, things like that. You can measure stuff where you have an image and you see there's a circle in there or a square, and you would like to know what is the diameter of the circle, stuff like that. Apply different transformations to an image. The feature matching I have already mentioned, or then segment an image where you try to label different regions of the image, saying as this is one thing, this is another thing. So far so good? Cool. And the way this is done is through different submodules that contain most of the methods. So if you just import skimage, it will only give you a bunch of utility functions. You really have to go into these different submodules to get to the meat of it. So there's a submodule that provides some test images, example data, very useful. There's some input-output stuff for reading, loading images, stuff like that. Some color transform, filters, and some more advanced stuff that we would maybe consider more computer vision instead of image processing, beyond measuring, which is feature detection or restoring images or segmenting images. So we're going to walk through some of these in code so you can get your hands on and actually use them rather than just seeing a list here. But this should be a nice overview to give you an idea of what's possible. Okay. So how are images represented in Python or in scikit-image? It is as NumPy arrays. So you're already familiar with NumPy arrays, I assume? Cool. So we could create our own image which is basically just a two-dimensional NumPy array. So what I've done here is I've created a 5x5 matrix. It all has ones in it. And then I overwrite certain elements in the image, which now correspond to pixels with different values. So what should this look like? It should look like something like this. Here, black stands for 0, white is 1. You can see that the first pixel top left I set to black, and here the third row, so we're indexing row then column, we turn black. There's two different ways you can do it, either with integer precision, where every pixel is between 0 and 255, or with floating point numbers, where every pixel is between 0 and 1. Loading images is then straightforward. So you import this IO submodule, and you call image read on a path to a file. You can also just load it as a grayscale image if you want, by passing an additional classifier. And you can save any NumPy array as an image by calling imsave. Yes, and since scikit-image actually operates on NumPy arrays, you can use any image reader library that you prefer, maybe Matplotlib or Pillow, whatever helps you creating a NumPy array of an image scikit-image can read. It's also easy to draw stuff on images with the drawing submodule, just mentioning this so that you've heard of it. So you can easily draw lines or circle, polygons, or even random shapes onto an image. So to get our hands dirty, put together a little tutorial where you guys can try out some stuff. I'll walk you through some things. And this is all contained in a repo that I put together on GitHub. You can either download it to your computer or run it on the hub. So what I'd like you to do is, I'm running it locally. So let's say I'm navigating somewhere where all my stuff is. It's in Documents GitHub. And in there, I run the clone command. And that will create a directory wherever I'm at in documents/GitHub with all the code. I'm not going to run it here because I already did. This is how you do it. Everyone got the URL? Cool. So then this will create a local folder called 2018-neurohack-scikit-image. And in there, there's a bunch of stuff. Most of it is for the website, the slides that I'm running through. But there's also a tutorial subfolder, which has a bunch of Jupyter notebooks in them. So the next thing I'd like you to do is fire up Jupyter Notebook. As I said, I'm running it locally, so you would achieve that just by what? Typing Jupyter Notebook. And that should open up a new window in the browser. Eventually. There we go. So I could have done it from the local folder where I was at. I didn't, so I have to go back to my folder 2018-blah blah blah. In there, tutorials. And in the tutorials folder, the first tutorial with the 1 is the introduction. Everyone got to that point? Cool. All right. So, is this big enough? Can you read this? Okay. What we want to do first is just mess with a bunch of NumPy arrays to create some images. So if you don't remember, an easy way to step through these notebooks is to click in a cell and then hit Shift and Enter. This will execute the cell and then also select right below it. So if I do this, it will run the cell. The first one is just generating a bunch of noise. We can see here an image 500 by 500 pixels. And we're plotting it using matplotlib. Did you guys already cover matplotlib? A little bit? A little bit? Who's familiar with MATLAB? Who's still using MATLAB every day in their research? And who's thinking about switching to Python? Cool. So matplotlib is basically started out as a clone for the MATLAB plotting functions. We usually import it with the command like this. In matplotlib, there's a sub module called pyplot that we import, and because that's really long, we just usually import it as PLT convention. And then within PLT, we can do a bunch of stuff, one being imshow, which is basically plotting the image. And you can also specify a color map for this image. Here we're saying it's grayscale. There's other stuff like jet should work, which has like the old standard color map of MATLAB. But because this is just a one-channel grayscale image, we want it to be plotted as this. So this is just to show that we can create our own NumPy arrays. We can also load stuff. Scikit-image provides a bunch of examples, data examples, image examples in data. So one of them is called coins, and we could just grab coins here and imshow it, which will create another little window like this. And you can see it's an image of a bunch of coins. There's a bunch of other attributes printed here, which tell you the type of the array. Well, it's a NumPy and the array, fair enough. And it has precision uint8. So 8-bit integer, which means we're expecting that every pixel value here is between 0 and 255. And if we print the shape of the image, we see returned here 303 rows, 384 columns. Piece of cake. It's another image we could load of a cat. Now this one here is an RGB image. How do you store that? Well, there's 3 different channels, an R, G, and a B channel. So if we plot the shape of the image here, we get number of rows, number of columns, and then number of color channels, 3. And so because these images are NumPy arrays, we can easily mess with them. Like if we wanted to plot a red square somewhere in there, we could just slice the NumPy array, specify like we want to print from rows 10 to 110 and columns 10 to 110, all channels, make them red. And what that will do is print a little square. Down here, so if you haven't talked about matplotlib a lot, let me just tell you a sentence or two about it. What you can do is create subplots, kind of like MATLAB does. So I think in MATLAB you would do subplot 1, 2, 1, and it would stand for 1 row, 2 columns, the first image, and then you plot something in there. So if you do this, and I hit Shift Enter, this will not work because I haven't executed the top cell. So if I execute the top cell first, image 0 is defined. I print image 0, I plot it, and this works like this. And there's another subplot in here that has nothing in it. A better way of doing this is to use this subplots command, where you can specify how many rows and how many columns you want and how big the figure should be. And then these here are returned as axes, where in the first axis you can print, or you can plot the first image, and the second you plot the second image. So what we've done here is we've just plotted the cat. On the right, we plot a rocket, but we also mark 2 different vertical lines. So this is just to show you that we can mess with these images pretty easily. It has nothing to do with scikit image yet. It's really just all NumPy. As I mentioned before, you can also draw stuff on the image. Now we're using scikit image. So we import to the draw module, and we call circle to print a circle. So if you can't remember what all these numbers stand for, there's a trick in Jupyter Notebook to show you the help of the function. You remember what that is? How you can do that? Question mark is one way. Yeah. So we could do draw that circle, question mark, and we hit Shift Enter. And then that won't work. Why not? Yes. Import. Do this again. And then this will print a little help window down here. There's another way, an easier way I find, because it doesn't create an image, is you go to the line where you want to be, the function call you want, you click inside the parentheses, and then you hit Shift and Tab. And that will open up just a little window like this and tell you the doc string, so what this function is about. If you hit Shift and then Tab, a tab, 2 tabs, you get the extended documentation. You can scroll down and see what's going on. So here we see, in order to create a circle, we have to specify the radius, no, the row, and the column where the circle is centered, and then the radius of the circle. So now I'm hitting Shift and Enter to execute the cell. And what we've done here is we've taken the image from before, which was image 1, the rocket, and we've used the coordinates that circle returns, which are a bunch of row and column coordinates, and we set these in the second channel here, the green channel, to 1 to generate a green circle. You can play with this later. Just wanted to show you this. If we scroll down past all this stuff to image IO, if you're still with me. In image IO, we can now easily read and save images using imread. So we're doing this here for an image that I have included in the repo. If you execute this cell with Shift Enter, you should see the scikit image logo. Interesting to know is you can also load a whole collection of images using image collection and just specify a wildcard here saying that you want all JPEG images. And when you do that, what this return argument IC will contain is a list of all these images that I've found. Cool. So far, so good. So let's say now we want to look at an RGB image and look at the color channels individually. So we know here the scikit image logo is an RGB image. We load it into image, and what we would like to do is plot each channel, each color channel separately. So if you look at the code that follows in this cell, there's a bunch of axes here, and these different axes supposedly print R, G, and B, which should stand for just this channel of the image. But if you run the cell, it won't work because there's some stuff missing up here where 3 dots are. So I'd like you to fill in these 3 lines of code so that R contains just a slice through the image that contains just the R channel, the red channel, the same for G and B. And if you're not sure how to do it, you can turn to your neighbor and see if he or she is better at it. Now I'll start typing too, in case this is kind of boring. So we know an image, an RGB image, has 3 different dimensions: rows, columns, and number of color channels. So if we want to just grab a slice through the red channel, we want to select all rows, comma, all columns, and then the first channel, which is for red. And then we do an analog thing for the other 2. Analogous. Like so. And if we run this now, what should happen is we get 4 columns down here. The first one is the red channel, green channel, and blue channel. And then the last one is all channels combined. This allows you to obviously mess with the channels individually. Like if you think back to the image of the histology image of the cell tissue that had 2 different stains in it, you could look at individual channels of this image and then just process that if you want. Of course, the first 3 are just grayscale images because they just have 1 channel. Make sense? Okay. Then let's move on swiftly to some more interesting stuff. And I'd like to talk to you about 2 things for sure. We'll see if I have time for the third, which are filters and features. I'm sure you're familiar with filters. It's a very common image operation. You probably have heard of a Gaussian filter. There's other stuff like the sobel filter, which people use for edge detection, and more fancier stuff like a median or a gabor. If you're not sure what filters are, it's basically about a convolution. So you think about an image. It looks like this. And what you want to do is apply to each low region of this image a small, what we call kernel. So maybe this is a 3x3 kernel. And what you want to do is do a local operation using this kernel and repeat it all over the image. So one of the easy filters, let's say, so this is now my kernel. This is the little image that we convolve the image with, I want to say. If we did something like this, the local operation we do is usually a dot product. So you take this mask, this kernel, and put it over the image at one location, and you compute the weighted sum. So you do 0 times whatever pixel value you have for the image, plus 0 times whatever pixel value over here, plus. And that you sum up, you get one value, that's your output value. So if we had an image and we convolved it with this kernel, what would happen? You get the image back. Because what this says is do nothing except for the center and just take 1, the value 1 of this. So you can do fancier stuff. Like what if we did something like this, 0, and then, oh, I don't know, maybe something like that. Or it doesn't need to be a 2, we can just make it a 1. What would that do? So what this is trying to do, so it's looking for vertical edges, basically, right? So the weighted sum of this will be greatest if you have something that is oriented along this little filter, right? Going from negative to positive values. And if these 2 guys are 2s, then this is actually a sobel filter, which we'll talk about in a second. You can form more complicated filters like this. For example, a Gaussian filter is kind of like taking the mean of a local average, but the values in this kernel are actually following a Gaussian. In a scikit image, you don't have to do a lot of math or anything. You just open the filters module and call Gaussian filter. You can specify this, the sigma, the standard, the size of the neighborhood, standard deviation of the Gaussian, as an optional argument, and that allows you to apply different Gaussian filters to it. Effectively, what happens is you blur the image, as you're probably aware of. The larger the sigma, the more blur. Going back to this little filter, the sobel filter is what I just drew over there, except there's twos in two locations. It allows you to find edges in the image. One of them looks for vertical edges and the other for horizontal one. This one, of course, looks for vertical ones. And this one over here for horizontal ones. You can combine the two edges to get an idea of the overall gradient in the image, as is shown on the right. So if you start from some original image and you apply the sobel filter, what you get is something like this. So here you can see that the edges are enhanced, and they're enhanced in different ways. So it's not just a binary output. Depending on how steep the gradient is in local neighborhoods, the output of the sobel filter is much stronger in some places than in others. There's other games you can play, like a median filter. What it would do is, if we think back to the kernel, it would just look at all the pixel values in this small neighborhood, calculate the median pixel value, grayscale value, and replace all the pixels in this neighborhood with that very median value. What that can do is remove noise from an image, as you've shown here. If we just do this in a 1 pixel neighborhood, then we don't get much enhancement. But as we increase the size of the filter, we get a more and more blurry and a more smooth image. It's actually a fun thing you can do with this is produce a cartoon effect. If you're following along the slides and you want to look at it, it's a little blog post to put together. Just blatant self-advertisement. You can do stuff like this, kind of smear out different colors. Of course, you have to draw in the edges, but you can sort of cartoonize the image. Anyway, what we really want to do is use these filters to extract information about the image. I already told you about one thing we could do is we could find edges. That's one feature. Other features are, for example, corners or blobs. And this is just to show it's really hard to say what a feature really is and what it all means. You have to imagine this is from way back when people were engineering algorithms, right? And they're looking at these different images and trying to quantify, like, what are the interesting parts of an image? How can we quantify that? So what they would do is use some sort of method to ask at every point of an image, is a feature present or not? So if we did the thing with the edges again, we would ask in every local neighborhood, is there an edge or not? And what we get out is a nice binarized edge map. For example, as shown here. So one algorithm is called the canny edge detector. And maybe to give you an idea of how it works, or how is it different from just a filter. So before we were talking about the Gaussian filter, for example. And this is just one mere step in this algorithm, if you want. So that makes canny edge detection more of an algorithm or like a feature detection method than a plain filter. What it would do is it basically finds intensity gradients, so edges again, and it picks sort of good edges. Because as before with the sobel image, we had an image where certain edges were stronger than others. What canny tries to do is find the edges that are connected the most and highlights them, as seen on the right. Don't want to go into the details. We can play with that later if we have time. Oh, sure, yeah.
So if you have a color image, apply the filters to each
Yeah, so canny usually only works on grayscale images. So if you have an RGB image, you have to get creative. Either you convert it to grayscale, or you as like the engineer behind it decides that no, actually every individual color channel is important, and then you could apply canny to every color channel. But there's no clear-cut answer. All right, another feature you might want to extract from an image is a circle. And this is kind of an involved method, so I'll just briefly mention the Hopf transform. The idea here is that you could parameterize a circle, as shown here, and you could ask in every space, in every pixel location of the image, is there a circle present? So you kind of vote in every location, could there be a circle, could there be a circle? You do it for all possible radii, and in the end, you return the circle that is the most likely to be there. That's all I'll say for now. We'll come back to that. Just to show you there's more involved features, like the Haar wavelets, for example. If you're into vision neuroscience, then this might look very familiar. So this is something they came up with to perform face detection. The idea is, how can you differentiate different faces? And they came up with this method of just looking at small local neighborhoods of the image, small rectangles, and just kind of counting pixel values in these rectangles, and then taking the difference between those. And that sort of stood for like a descriptor of how much variation you had in that local neighborhood. So if you did that with all possible sizes, like shown here, and with all possible directions, you will get a very rich description of these face images. And if you fed that into a classifier, it might have a better chance than just looking at the raw grayscale images. There's many more algorithms in Scikit-Image that are just there, available for you to use to detect corners, for example. There's another one to detect gradients, local gradients in the image, and then other more conventional, creative conventional descriptors. Kind of before ConvNets came around, people had to actually come up with, engineer these features, right? And nowadays it's more common to let the machine figure out what are the important descriptors. But enough words, I really would like you to play with that. So there's another little tutorial I'd like you to run through. If you go back to where we were in our tutorials folder, the next one should look like this. It's called feature detection. And Ariel, do I have till 3:30? All right, we'll do this. Okay, to show you how this works in Scikit-Image, I have already run this. Why haven't I? Let me just clear all output. And then we start from scratch. Cell 1, shift and enter. Move through all of these. What we're doing up here, we're just messing with matplotlib, setting a bunch of settings for like the color map or other options. Where things get interesting is down here in this cell, where we load an image. This time it's a camera image. It looks like this on the left. What we're doing here is we're loading an image, and then we're grabbing only every 10th pixel along the rows and along the columns. And what that gives us is a pixelated version of this higher resolution image. We can look at the original one. If I enter a cell up top, it looked like this, a man looking through a camera. And if we only grab every 10th pixel of this, it looks like that on the right. And so what we can do is just detect edges using the sobel filter, which is in filters.sobel. And if we again click into the parentheses and hit shift and tab, we can look up the help for this function. It tells us find the edge magnitude using the Sobel transform. And what it really wants is just an image as an input. And optionally, you could specify the mask as I've drawn it over there to be your custom choice. So when we apply the Sobel filter to this pixelated image, what we get is basically shown on the right. So we store it in a variable called gradient. And when we look at it, it looks like this. You can see that some edges are stronger than others, like back here. This is very faint. But it all depends on the gradient in this local region. Like here, we're going from very bright to very dark. And that's why the edge is weighted higher than here, just going from sort of dim to a little less dim. And there's text for you to read through later if you want. What we can do is, with this, is we can apply our own thresholding algorithm, for example. If we really just want the foreground, the man looking through the camera, and not all this background, well, maybe what we really want is just to grab these really strong edges and not these other ones. So we can do this by adding a little threshold, saying we just want a binary image, really, where all pixels are true, where the gradient is greater than 0.4, and everything else is black. But when we do this, we get something like that, which doesn't really help us. So if we wanted to detect the edges in all the edges, the important edges in this image, we have to do something smarter. And this is again where the canny edge detector comes in. So the different steps here involved are first a Gaussian filter, then the Sobel filter, then some other stuff. Now, why would we want to apply a Gaussian filter first? Remember, a Gaussian filter blurs the image. So here the idea is that if we just look at the gradient of any image, if that image is noisy, then we're going to amplify noise in the image, because there might be edges in there that we don't really care about. So one way to get rid of this is to first apply a Gaussian filter. And the result looks like this. As we know, it blurs. And then we look at edges in this blurred version. So if you run the next cell, it applies a Sobel filter on this smoothed version of the image. And what we get out is something that now looks much better in terms of the true edges of the image than we had before. I would like to skip through to the end of this. So there's a little tutorial that walks you through every step of the canny detector. Of course, Scikit-Image also provides the whole thing boxed right here. So if you run this won't work. Because we need to import again. So I need from image import feature. And now when we run the canny detector, what you will see is a clear image of all the edges. Here, all the edges are 1 pixel wide, and it's a binary mask. So the canny edge detector is really certain about this is an edge or not. Of course, its certainty doesn't help us because it's still adding a lot of noise here. So we would have to do further processing to get rid of all this stuff. What did I import? Feature. Canny used to be in filters, but now it's in feature. Because they realized it's more of a feature detector. Okay. There's a fun one following, which we won't have time to do, which is about circle detection. Just to show you what it's about. this might pop up maybe in your research too, where you have certain structures in your image. Maybe, again, you're looking at an image of cell tissue, and you can see the nuclei of the different cells, which are sort of roundish. And maybe your job is to count all the cells in the tissue. So you could either sit there for a week and label them by hand, or you could use the Hoff transform, which tries to find circles in the image. So this is done here in an easy example for coins, but could also work on more complicated ones. But in the interest of time, I'd like to tell you just a little bit about image segmentation, which gets a little closer to the computer vision idea of really extracting scene information from an image. So ideally what we want is something like Terminator vision, right? Where we see an image and we know exactly, oh, that's a dude right there in front of a bar. He's holding a beer can. He's this this tall, and weighs as much, blah, 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 stuff like that. All information extracted from a single image. And there are lots of different algorithms to segment an image. So it's kind of hard. One class are supervised algorithms, where the idea is you provide some a priori knowledge to help an algorithm, or unsupervised, where you just let the algorithm do its own thing and try to figure out what's going on. One of the easiest ones is thresholding. So if we go back to the photographer, we could think of maybe there's a single threshold of pixel values that separates the foreground, which is the man with the camera, from the background. And one algorithm that does this is called Otsu's method. So it looks at the histogram. Here we have pixel values going from 0 to 255 and the counts of pixels. And what Otsu's method is trying to do is it assumes that there are two different classes of pixel values in the image. And it tries to find the threshold that separates them best. So it's looking at how much variability there is between two classes, and tries to maximize that while keeping the two classes as close to each other as possible. So for this case, we can see different bumps here. Maybe what we could have done is we could have chosen this value here, where we would say everything below is background, everything above is foreground. But maybe if we go here, then we see that we have a much larger separation from this one class of pixel values and this other class. So if we just use that and threshold the image, we get something like this, where you can now see that the important stuff here really is on one side and everything else is gone. A little more involved is the random walker segmentation, where the idea is that maybe you know beforehand how many different regions you have. Maybe there's like a dark and a bright one, but the image you have is really too noisy to just apply thresholding. So what you would do is you tell the algorithm, you give them different markers, like different seed points in the images, and you tell it it's either a dark or a bright region. And then starting from all these points, the algorithm sort of uses a diffusion process. So if you have 2 points, it will start to grow regions until they hit each other. And then those are the boundary finds. And when you do that with all these points here, what it will come up with is something that looks much closer to what we want, where you are able to differentiate between these bright regions from the dark regions on the side. Similar idea is the watershed algorithm, where you imagine the grayscale values of an image is now, you kind of put it on the ground, it's now a landscape. So you have brighter pixels are hills, and then dark pixels are troughs. And what watershed does is basically it runs water into one of the basins and lets it slowly fill up. So what you can do is, again, provide seed points, like say start here and there, 2 different basins, and you fill up water, and then these are all connected regions because they have similar pixel values, similar topography, and you just let the water rise until it hits, and then that's your boundary for the segmentation. There's other fun stuff, or slick stuff. It's basically k-means clustering, where you have to tell the algorithm how many clusters you're looking for. and then it will automatically cluster different pixel values, as shown here. What you get are so-called superpixels, which are not really individual segmented regions, but they're much larger than 1 pixel. And you can see they follow the boundaries pretty nicely. And many more algorithms. So the point here is that Scikit-Image implements most of these in a straightforward manner, so you could just apply them with like 1 or 2 lines of code and try them on your own images. There's another tutorial which we won't have time to run through, but it applies some of these segmentation methods in Scikit-Image. Maybe to just give you a glimpse at it, it will tell you how to run. Here's the Terminator again. It will tell you all the different algorithms that Scikit-Image implements. There's some code for thresholding by looking at the histogram. Maybe I could just run most of this, show you the output. So for example, if you're looking at text and you just want to segment foreground from background, you would look at the histogram and find the threshold that best separates 2 blobs. And when you do that right, you get a nice classification. That won't run, whatever. And then there's some other code that will run you through the watershed algorithm and through the slick algorithm, as well as some more advanced stuff. So if you're interested, yeah, have a look at it. And maybe later, if you find that Scikit-Image is something that could help you in your own research, be it just to denoise images or sort of pre-processing for some other more involved step, you can come back. There's a lot of cool tutorials and examples on scikit-image.org. This is the landing page. Up there is gallery. And the gallery has a lot of examples of how to run this stuff. On top of it, there are some tutorials which I drew from for my own little tutorials, which you can look at as you go along and make sense of this. And just to mention, Scikit-Image is, of course, only one library that can do image processing and computer vision. Another popular one is called OpenCV, which is often used in like the robotics community. The difference between the two is that OpenCV is implemented in C++, so it's a lot faster than Python. So if you need something that's fast, you go with OpenCV. But if you need something with a consistent API, I would say Scikit-Image is the better choice. And that's it. Do you have any questions? Yeah?
Is there anything for like time series image processing? Supposedly, you have a microscope, you track 96 seconds.
And you don't just want to look at every frame individually?
Yeah, like on a per frame basis, you want to identify a feature, or you want to
Yeah.
denoise it. It's like
Yeah, it gets kind of involved at this point. Do you know a good one?
There's one that
There's yeah, DaiPy.
nighttime.
Yeah.
Complicated.
Yeah. I mean,
Yeah, it depends a little bit on what you want to do. So yeah, depending on what kind of analysis you want to do, you might need, if you need sort of statistical modeling, like or regressive modeling, there's something called stats models, which is pretty good, but it doesn't think about things as images necessarily.
right. And if you want to do stuff more like, well, either regression or classification, then maybe a recurrent neural network might be something like an LSTM or, yeah. But it really depends on the use case. Anything else? Okay, that's it.
Thanks a lot.
Thanks.